So good afternoon, everyone. We are Group 6. We are Amro Ghoneim, Marla Ebeid, Zeyad Hesham, Nour Hashad, and Ahmed Ashraf. And we have a video here and hope you enjoy it.
Okay, good afternoon, everyone. So our topic is the multi-tier machine learning platform for IoT devices. So we'll start with a quick recap of the problem definition. So traditionally, all the machine learning models and the data analytics were hosted in a centralized server or a centralized cloud. All the data was put in one central location to facilitate all the pre-processing tasks, as this aspect made it easier. When the big picture was all presented in a central server or a central cloud, this allowed for a more generalized form of the data. However, due to the huge rise of the IoT devices, and as the right figure mentions, this is the forecast expected by Ericsson.com of the rise of the IoT devices in the upcoming years in billions. So transmitting all this data back to the central servers would not be easy due to the huge amount of the data, and aggregating it, processing it, and providing useful insights in real time would be difficult because due to the huge size of the data incoming. So basically maintaining the traditional central-based model or the usual central-based architecture would simply be infeasible. Our proposed solution is a multi-tiered machine learning framework, which that its goal is to push the real-time analytical tasks towards the edge devices of the network, or even towards a secondary tier, which is the gateway, while still maintaining our central system to basically reconcile with the most important events, which will be compressed or a compressed version of the data to provide more in-depth analytics later on, as we will explain. Similar systems to what we are trying to implement are the Google AI and the Clarify. So basically for the Google AI, the server randomly selects a number of connected edge devices and downloads a machine learning model on those edge devices. The model is trained on local data. However, it's summarized and keeps on getting updated. Clarify is a company that specializes in computer vision, and it also uses machine learning and deep neural networks to basically identify and analyze images and videos. Clarify basically has a distributed platform where users can connect to the cloud to retrain the model. This basically is similar to what we are trying to implement because we have the capability of retraining the model back on the edge device, similar to Clarify, which where real-time prediction and inference can happen directly or can happen offline, or there's also the option of prediction happening online where the data can be sent to the cloud for retraining and then sent back to the edge device once more. So if it's used, basically it has like a low latency that enables real-time inference. However, both Google AI and Clarify are different from what we're trying to implement in the sense of that the data is not thresholded. So basically we don't send all the data to the cloud in our case. We use some sort of a threshold to decide whether this data is of importance or not and whether to send it or not in the first place. And now Ahmed will talk about the system diagram.
As you can see, this is the diagram of our system, which consists of 3 tiers as mentioned earlier: the edge, the gateway, and the cloud. These are the sensors which are going to capture and send data to the network edge devices. Inside each edge device, we have a filtering algorithm which passes only data with important features to the prediction module, which we're going to analyze, further analyze these data in order to take an action. These data are stored on a memory module on the edge device for retraining. These data are sent to the gateway. The gateway aggregates all the incoming data from multiple edge devices on the same network, so it can retrain the model on these aggregated data and sends back the updated weights to the network edge devices. Between the gateway and the cloud, the gateway sends these data to the cloud aggregates these incoming data from multiple gateways for further analytics and retraining of the model, so it can send back the updated weights of the model to the gateway, so it can improve the performance of the model. For our use case, our use case is vehicle collision detection. Our sensors in this case are video surveillance cameras, which send streams of frames to the network edge devices. In the edge device, we have again the filtering algorithm, which passes only frames with potential accidents. Then these frames are passed to the prediction module, which furtherly analyze those frames and check whether those frames include or have accidents or not, and outputs or gives the prediction. Both models are based on logistic regression. As mentioned earlier, the data is sent to the gateway, which retrains the data. The retraining and model on the gateway is based on also logistic regression. We decided to remove the third tier due to some limitations in hardware. We wanted to have multiple gateways so the cloud can aggregate incoming data from those gateways. However, we have only one gateway. So if we included the cloud in our experiment, that would create a redundancy because the cloud receives data from just one device. Now, moving to the communication model. This is the model architecture we wanted to achieve. N networks connected to the cloud. Each network consists of N IoT devices connected to one gateway. For the communication protocol, we explore different protocols such as HTTP, CoAP, MQTT, XMPP. When it comes to the choice of the communication protocol, there is no best and worst. Actually, it's based on the nature and the needs and the requirements of the project. We decided to use MQTT. MQTT stands for Message Queue Telemetry Transport. It's a publish subscribe, extremely simple and lightweight messaging protocol.
For the communication.
MQTT nature makes it perfect for our system as we can connect one device to N devices and vice versa. MQTT provides ease of management, data organization. MQTT is extremely reliable. It's lightweight. It has various quality of service levels to ensure, again, reliability. It offers simple ways of authentication and access control. How MQTT works and what it is composed of. The client, which is the connecting party, or the communicating party. The topic, which is the channel which the clients publishes and subscribe the data on, and of course the message. And finally, the broker, which is the most important part of MQTT, and actually why we chose it. It can easily scale, the broker can easily scale from a single device to thousands. It manages and tracks all client connections, including security credentials and certificates. It eliminates vulnerable and insecure client connections. It reduced network strain without compromising the security. This is the two-tier communication. The Jetsons subscribe to a channel and the gateway, which the gateway publishes on, and it's the same backwards. The Jetsons publish to a certain channel and the gateway subscribes to it. For the message format, the data, which includes the prediction, are saved in the following format, this format, as a byte array and sent to from the edge device to the gateway. For the communication or the message format backwards, we have the updated weights, on a hierarchical data format, which are transformed into a byte array and transmitted back to the edge device. This is the overall communication diagram. N Jetson devices or IoT devices connected to a broker, connected to the gateway, and N networks are connected to the cloud.
And now, Zeyad is going to talk about the improvements we did to the system.
Thank you, Ahmed. Okay, so to improve our system, we tried to use multi-threading. Multi-threading is the process of generating multiple threads to increase the speed of the system. However, in Python, the global interpreter lock, or the GIL, is a mutex that protects access to Python objects, therefore preventing pure multi-threading. That is why when multi-threading was used, our system's performance did not drastically improve. So what we did instead is use multiprocessing. By multiprocessing, we are using more than the 2 cores generally used. We are using all the 4 cores of the Jetson Nano. Enabling multiprocessing allowed the frames per second to increase from 18 to 22 frames per second. This is due to the fact that now all the processes are distributed and are not executed in one thread. This allowed us to save data on the edge devices without decreasing the system's performance. Finally, it allowed for synchronization between processes using queues. On the edge, we have 5 main processes. The inference process sends data, which is in our case all the frames coming from the feed. The save data process saves the frames and sends 2 flags. The first flag is sent to the send data process to be sent to the gateway. The other flag is sent to the train model process to start training on the frames. Finally, the receive data process sends back the received weights. On the gateway has 5 processes as well. The receive data receives the data from both the edge and the application. The data received from the edge is sent to the application for monitoring, and any data sent from the application is an updated data. This data is then sorted and trained on again. The new weights is then sent back to the gateway. And now Marla will be talking about multiprocessing on the desktop application.
Okay, so we developed our desktop application, which is the external input in our system, using PyQt. These are the functionalities of the application. First, a user can trigger an alarm whenever there is an accident that was not detected by the system. He can also reject an alarm in case there is a false detection. The user can view all the frames of interest along with its timestamp, frame ID, and Jetson ID. The last functionality is that a user can change the label of a frame, whether from an accident to not an accident or vice versa, and this updated frame will be sent back to the gateway. As for multiprocessing on the desktop application, the data is received from the gateway as frames, and then each frame is displayed along with its ID, Jetson ID, timestamp, and flag. And this flag shows whether this frame is labeled as accident or not. So the user can update this flag, then the updated frame will be sent back to the gateway. We were able to achieve synchronization by sorting the frames that comes from the Jetson with respect to their timestamps, as you can see in the below figure. We wanted to do that so that we can use any model that uses temporal features so that it will receive the data synchronized. As for the system deployment, we wanted to containerize the system, meaning that we wanted to package the application along with its libraries, requirements, and configuration files so that it can run on various computing environments. Why we wanted to do that? Because containerization is faster and more flexible than virtualization. It removes the overhead of our virtual machines. We use Docker for that. As you can see in the below figure, this is how Docker works. We package all the configuration files and requirements, then build the Docker image, push it to the Docker hub, and on every device on the system, we pull the image and run it. If the system required any updates or modifications, containerization allows us to do it just once and deploy it on all the devices. And now I will leave you with Nour, who will tell us more about our data set.
So the dataset we are using is the AI City Challenge dataset. This dataset basically comes from multiple traffic cameras in the United States. It consists of 100 training videos along with 100 test videos. Each video is approximately 15 minutes in its length. The anomalies in this video could be in these videos could be due to car crashes or stalled vehicles. The advantage of this dataset compared to the original dataset that we were using at the start is that it takes into consideration the temporal aspect of time, because each video is basically in the same area and in the same place, which is different to the previous dataset where each frame came from different locations and different resolutions, different backgrounds, everything. So basically this dataset is an improvement in this aspect. Each video is annotated showing the duration of the anomaly in each video to make it easier. However, this dataset is not multi-viewpoint, so we have to use OpenCV to crop each frame from the right and from the right and from the left to make it as if it's a multi-viewpoint dataset. This is how we use OpenCV for the first edge device we crop, and from the second edge device we crop from a different position to make it multi-viewpoint. Our final model was implemented using the machine learning libraries Keras as long as sklearn. So for our final model, it's a logistic regression model. So basically, what's logistic regression? Logistic regression is a model which is based on the probabilistic sigmoid function. Each feature is assigned, the features are assigned basically specific weights, and then they are used as an input to the sigmoid function. And what the sigmoid function does is that it produces a probability of the event occurring, and based on the threshold that we decide to set in the model, if the probability, for example, is above this threshold, then we predict that this frame shows an anomaly or an accident, for example. However, if the probability outputted by the model is below this threshold, then we decide that this is not an accident or this is a frame where no anomaly occurs. So why we decided to use the logistic regression in the first place? First of all, we were thinking about using deep neural networks. However, logistic regression is much less complex than neural networks. And this makes it an advantage for us due to the limited resources on the edge device. So on the edge device, using the neural networks would be a bit difficult to, in addition to the fact that neural networks need a lot more data than the data we have. Running the logistic regression on the edge device would be more computable because of the limited resources we have on the Jet and Nano. Also, it's best to use when the classification is binary, meaning like only two possible outcomes, either it's an accident or it's not. And we do not need to scale our features. Now Amro will talk about the methodology.
Okay, so for the methodology of the experimentation, this is what we did. We basically started with 2 videos for testing and training, and then we converted them to frames, and then we did some other pre-processing tasks such as resizing the frames and also normalizing the pixel values between 0 and 1 and converting them to grayscale, and all of this to allow for better training and testing and faster as well. And also after that, we take the data and give it to an algorithm that can crop the data by a certain percentage left and right. And we use that to synthetically create our multi-view data set as discussed before. And then we use the 2 data sets to train the 2 models on the edge, edge 1 and edge 2. And then we combine these 2 data sets together to train the centralized model. So this is the first part of our experiment. And then for the second part of the experiment, what we do is we use the 2 models on the edge, edge 1 and edge 2, with different threshold values. And for each threshold value, we see that a certain amount of data goes through the system. And as you lower the threshold, for example, you get more data flowing through the system. And for each threshold value, we test the same metrics that we used on the centralized model and compare them. And we will see this throughout the results. Okay, so for the first part of the results, as you can see here, the centralized model on the left, you can see the metrics that we used, which is the accuracy, precision, and recall. And as you can see, we have high precision and low recall, which basically means in layman's terms that we can detect an accident if it occurs, but we will most likely also give out false positives, which means that we will give frames with accidents, even though there were not any accidents, right? And then on the right, you can see that we have the 2 models, edge 1 and edge 2. And they have somewhat comparable metrics to the centralized model, which is expected since we are using the same logistic regression model to train all of them. Okay, so for the second part of the results, as you can see this graph, so the values below the 0.12 and all that basically means that, for example, 0.4 means that we use 40% of all the data going through the system. So it's only the threshold values that we use only allowed, for example, 40% of the data to go through the system, or maybe 60% or 80%, and so on and so forth. And the y-axis basically shows that if you get 100%, you are essentially performing with the same accuracy, precision, and recall as the centralized model that gets all of the data. Okay, so as you can see, around 0.6%, 0.6, which is around 60% of the original data, you get almost the same results, but with 40% less data. So you, using the threshold value here, you considerably use less data, and again, you get quite good metrics compared to the centralized model that we have. Okay, so this is for the demonstration. We have a video here that we will show you. So as you can see, this is the first video, and it can actually detect the accident correctly, but as you saw, it throws some extra accident frames, as you can see here as well. So again, it is able to detect the accident, but throws some extra accident frames. And then for this video, you can see that essentially it cannot capture the accident. So as you can see in this video and this video as well, it does not happen. So no accident over all of the frames. Now these frames that you see here that are synchronized and sorted past the threshold value, and they were extracted from the edge, from the gateway device. And then we use, as you can see here, the desktop application to retrain these, to retrain the model with these frames after relabeling them with the correct labels. And this is, if I remember correctly, it's called active learning. And as you can see now, these are the test results after retraining the model. So as you can see, it is able to detect the accidents. Granted that we are using the same training and testing frames, but again, we will be using the same context, so we will probably have the same no accident frames and similar accident frames in the future, right? So anyways, so this leads us to this conclusion, which is 2 points, basically, which is that using our proposed system resulted in comparable metrics to the centralized model with considerably less data transmission, and we saw that in the second graph in the results, right? And also that we can use retraining to enhance the metrics, the system's performance and the model's performance overall, and localize to each and every single view, right? And finally, for the future work, we thought of 3 things. Firstly, the system scalability and modularity, to make the system modular, to add and remove any part of the system without affecting the performance. Also improve the model performance using maybe a different model that can detect important features, or using smarter feature engineering. And finally, adding the 3rd tier, which is the cloud tier, as we've said before. We removed that because of the hardware limitations that we had and redundancy, and maybe in the future we can actually implement that as well. So that's it for our presentation. Thank you.